My name is David Sankel. I am part of Adobe's Software Technology Lab. I'm a principal scientist at Adobe. And the title of this talk and its topic is Exploring Validity. So this is part of the Better Code series of talks that Software Technology Lab puts out. The last one that was in this room was another one of the Better Code topics. And I am part of this very cool team that makes up Adobe Software Technology Lab. And really anything that we come up with at conferences or whatever, I feel like it's really a product of what happens in this team, because we discuss these things, and this is where all these ideas kind of come from. And like a perfect example of this is last Friday, I gave an early version of this talk to one of the colleagues on the team and got some wonderful insights out of it and had to rewrite the entire talk. So I won't mention any names. Dave, don't worry, I won't throw you under the bus. I won't tell everybody it was you. So this is a talk that is about words, okay? We're gonna be looking at some words that we use when we talk about software all the time. We generally have a kind of vague idea of what they mean. And what I really want to do is to really dig deep into these words and get a good sense of what the ultimate meaning is. And I had a conversation with Andre, whose talk is after this one, his keynote, to tell him that he should be very happy that I'm giving this talk before his talk. Because all of you are going to be nice and well rested after your little nap during this talk for Andre's talk. I'll do what I can, but it's hard. So this is a slide from Bjarne's keynote earlier this week. And there were a lot of words in this slide, a lot of words in a lot of his slides. So it just so happens that he used some of the words that I would like to discuss. So we're going to start with this word right here, valid. What does valid mean? Okay, so if you think about it, just think about the word as you use it in the normal sense in English. Valid separates stuff into two categories, right? You're either valid or you're invalid. There's not really an in-between, right? So this is represented by these two squares up here, valid and invalid. Now, is that enough to capture what valid means in our mind? Is it just two categories? Not really, right? There's something more to it than that. There's like a judgment. One of these is way better than the other one. So here represented by the angel and this little demon here, but if we think about words like suitable, unsuitable, correct, incorrect, desired, undesired, there's a clear bias towards one of these two categories that is used when you talk about validity, right? Complete, incomplete. So now we have two things about validity that we can say. There are two categories, right? And one of these categories attracts you and one of them repels you. Just the words do that to you. So that means that there's really an aesthetic sense to these words. But even having the idea of there being two categories and this aesthetic sense, there's still something missing when we talk about validity. And it comes from the aesthetic sense, really. And that is that validity, just like beauty, is in the eye of the beholder, right? If we take this key and we say, where is this key valid, right? Well, it depends on the lock, right? This key, when it's put into the right lock, will open the door. If this key is put into the wrong lock, it won't open the door, right? So it depends on the lock to be able to talk about whether or not this key is valid. So zooming back out again, validity is these three things. The two categories, the attraction and the repulsion, and the idea that there's some kind of beholder. What does this have to do with C++? Well, I think that it very much relates to Dave and Sean's talk when it comes to contracts, right? When we have a precondition. So here's a square root function, it has a precondition that its argument is greater than or equal to 0, because this doesn't work with negative numbers. So in this sense, negative numbers are invalid arguments to square root. And a declaration of argument validity is called a precondition. When we say something is valid or invalid with respect to a function, we're talking about that function having a precondition. Does this match our intuition for validity? Well, I think it does, right? We have two categories, valid, invalid. One attracts, one repels. That is the valid sense. We feel much better about calling a function in a valid way. And it is with respect to a beholder. The beholder in this case is the function that you can potentially call. Given that, we can give a precise definition of validity. So an argument list, O1, O2, all the way to OI, is valid with respect to a function f if the function call, f of those arguments, does not violate any of f's preconditions. Now we have a definition of the word validity. An argument list not meeting that criteria is said to be invalid with respect to f. So we got the valid, we have the invalid, we see how they relate, we see how it connects. But what's an invalid pointer? Now this is something that we frequently talk about, right? We have it as part of our normal parlance. We have this idea of an invalid pointer. And here's a little piece of code that creates an invalid pointer. So we have it int pointer I, which we set to 0. And then we have another block of code where we create an int j set to 3, and I is set to the address of j. And then that block ends. What's the status of I? So at the end of this snippet, we say that I is an invalid pointer. But what's the beholder in this case? What is the thing, what is the lock which is saying that this thing is invalid? Well, I would say that it's invalid with respect to dereferencing, right? We cannot dereference this pointer. So when we say a pointer is invalid, we're really saying that it's invalid with respect to dereferencing. But keep in mind that when you say something is invalid, it doesn't mean that it's something inherent about the object, right? It's invalid with respect to that operation, but it's not invalid with respect to some other operations. You can take a so-called invalid pointer and you can assign to it. You can check it for equality with something. There are several things that you can do with this, right? And it's totally fine. It's not something that you can dereference. Keep that in mind. All right. What are some best practices on argument validity? And we're going to thread through some best practices that come out of this study. The first one is to document your preconditions, right? It's useful for a user of your code to be able to tell when they're calling something with a valid or invalid argument. The second one is that when you're discussing object validity, clarify what the associated function is, right? And this ties into the third one, which is when checking for validity is possible. It's not always possible, but frequently it is. Name the query after the associated function. So if you're thinking about using isValid for some kind of a smart pointer, maybe call that isDereferenceable instead of isValid, right? That's more clear. Or if you have a UTF-8 string, right, which can have some code points in there that totally mess it up, instead of saying isValid for that UTF-8 string, you can say isDecodable. Or if you have an input stream that's invalid, maybe you could call that isReadable instead. So do you see how this kind of makes your code a little bit more readable if you specify more directly what validity means? Yeah? Cool. All right, we've looked at valid. There's another word right next to this one that we can go into. What's an object? Okay, an object is an instance of a type. Sure. You kind of get a sense what an object is, an instance of a type, but it doesn't really give you a deeper understanding of what's the thingness of an object. What makes an object that object as opposed to anything else in the world? We want to find out what's the fabric of an object. And when I started doing this investigation, I thought that the fabric of an object is its state. Okay? Let's look at state. You have all this memory in your system, right? And you have some kind of object which is sitting in this memory. You can color in and you can point out the different pieces of information that make up that object, right? That can be its state. That can be its thingness. And here we have a struct P. It has a X and a Y, int 32s. And An object O of type P, its state consists of the bit configuration of O.x and O.y. That'll give us like what we saw on the previous screen. We're just talking about that, the bit configuration of that information. But what do you do if you have something like this? Okay, so this is just like the P on the previous screen, except instead of having int32 members, it has int32 pointer members for its x and y. And here we have x is assigned to, you allocate what you want the memory to be for your x variable, you allocate the memory for your y variable. The state of this object really can't just be the data members. There's more to it than that, right? That those data members point to some other memory, and we feel intuitively like this really should be part of this object state. And so our definition of state is going to include this. And the way that we do that is we say an object state is the bit configuration of memory that is under that object's ownership, right? Not just that object's data members, but all the memory that's under its ownership. And that gives us the kind of intuition that we want. So the bit configuration of an object O of type P, its state consists of the bit configuration of O.x, the bit configuration of O.y, the bit configuration of what O.x points to, and the bit configuration of what O.y points to. But look at this, like objects always have a state, right? Even in the middle of a function, even in the middle of the constructor. So what is the state of star this at this point in the program? Well, we have the bit configuration of x and the bit configuration of y, and the bit configuration of what x points to. But notably, there's not the bit configuration of what star y points to, because that memory hasn't been under the ownership of the object yet. Okay, so the idea of this is just to get the sense that objects kind of grow and they have this, they can change over time what kind of state, what their state looks like, all right? All right, but like I said, I started this investigation thinking that state was a thing. That's what made an object its itness, its stuff. But there are a couple of examples that really threw a wrench into this whole thing. I'm gonna look at those now. The first one is a string that's using small buffer optimization. Okay, so for those of you who haven't encountered this, the idea of a string with small buffer optimization is that in the object itself, in one of its data members, it has some storage ready to go. In this case, there's like 32 bytes available to fill things. So if you use a small string, you initialize this to a small string, it'll just put that information in data and it won't do any kind of allocation. But if you exceed that size, then what it'll do is allocate memory and then use allocated memory and just ignore what's there in the data member. So the destructor of string would look something like this, right? It says, if begin doesn't equal the address of data 0. In other words, if we're not using the small buffer optimization, then I need to make sure I delete what that memory that I allocated points to. Fine. But think about this in terms of state, right? In the state, I said it only consists of the information of the data members and objects under ownership. But here we see that in order to get the substance of this thing, I need to consider the address of the string, right? Now we're talking about the address of the data members and where it sits in the relationship between these addresses. So this kind of throws a wrench into the state thing. When I tried this and I gave this talk at C++ North, I said, okay, state also includes the address of the object. But then there was another example that came, and that made that even more confusing and not work. And that's this. This is a hash map that uses a global seed. Now I'll walk you through this. So the first chunk of code here, what it's doing is it's initializing a inline static global. And it's basically saying when this program starts, or when the first access of this global variable, what it's going to do is it's going to go onto the random device on your computer, which hopefully provides a lot of entropy and gives you like a real, good random number, super random, and assigns the variable to it. Okay? And then this secure hash map, when you insert a key value pair into this hash map, the first thing it's going to do is it's going to use std hash to calculate the hash of the key. Sorry, that should be hash of key. It's going to calculate the hash of the key, and then it is going to XOR that with that global seed. Now, why would anybody want to do this? Well, the reason is if you construct your hash map in this way, it makes it much more difficult for an attacker to do a hash collision attack and fill up your hash map and give you like bad performance through whatever reason. So the Swift hash map, by my understanding, it uses this kind of technique for this reason. But think about it. In order to understand this secure hash map, an instance of this secure hash map, I have to know what the value of the global seed is. Otherwise, I can't really fully understand it. So this is memory that's not even under the ownership of the thing. So state, it just doesn't work. So we know that the stuff of an object, it definitely includes the state. The state's important, but it may also include its address or relationships between addresses. It may include bit configurations of things not even owned by the object. So we need something new. We need something different besides state. And this is what I came up with. An object's substance is the information on a computer necessary to determine an object's behavior. Okay, and this actually neatly captures all of those things about state. Don't give me that look, Dave. And if you think about it, this is actually quite a beautiful thing, right? We're able to put a boundary around information that makes up an object's substance, right? Its thingness. We'll see how that plays out later on. So the substance can take on many forms. So let's say we have a struct P here, like we were looking at before with this X and Y. And what you see on the right are all the possible forms the substance of P can take. So if you have an X equal Y and an X equal to 3 and Y equal to 4, that maps to this particular point in all the possible substances that this object can take. If you have X equal to 1 and Y equal, or X equal to 0, Y equal to 1, that points to this indicates this other possible substance that this object can take on. And if you think about the lifetime of an object in your program, its substance is changing forms all over the place, right? So it just jumps instantaneously between these different possible substances that it can have. We have a sense of an object, right? Its substance. It's what defines the boundary of an object. But what is a valid object? This is actually a quite more complicated thing to discuss. So we have our substance here, all the possible substances. When we talk about some objects being valid and some objects being invalid, the temptation is just to say, okay, there's a subset of all these forms that this can take, and we're just going to call these valid forms, and we're going to call the other ones invalid forms, and just make an arbitrary decision about that. But you have to remember that when we talk about validity, it's always in the eye of the beholder. So we need to go into more depth in terms of what that looks like. Here's an example. We have a unique pointer, P, and we assign it to make unique int of 3, okay? Everything looks good. And then we have a call which says delete p.get. Does this look good? Raise your hand if this makes you really uncomfortable. Okay, good. Keep your hand raised if you think this is undefined behavior. It's not. There's nothing in the standard or specification which says that this is undefined behavior. Raise your hand if you think that this will ultimately necessarily lead to undefined behavior. Okay, most of you. Well, not necessarily, because I could do this. I can call p.release right afterwards, and now p is in a not uncomfortable state, right? Okay, so we get the aesthetic sense, right? There's clearly something that knots our stomach when we see that object after delete p.get, but what is it? What's the problem with it? Well, we define this idea of a discardable object, okay? A discardable object can be destructed or assigned to. When you delete p.get, that pointer cannot be destructed, nor can it be assigned to, right? It gets into a really nasty state. So our first idea of validity of an object is we put a circle around all the states which have that property of being discardable. If you're outside of this, it's just like crazy town time. Another way of stating this is that a discardable object's substance has a form that can be destructed or assigned to. And another way of saying that is a discardable object's substance has a form that meets the preconditions for destruction and assignment. But meet the preconditions for, we already said what that is, right? So we can reword this again to say discardable objects are valid for destruction and assignment, right? A nice concise way to talk about this kind of invalid object. It's invalid for destruction and assignment. Okay. It turns out that there's a subset of objects or of substances that are discardable that have an even stronger sense of goodness for us, right? And when we talk about this subset of discardable, we need to talk about class invariants, right? This is what makes up the smaller, even better looking set of substances. So a class invariant is a predicate over an object's substance for a particular type. And a stated invariant for a type implies certain requirements, which we're going to talk about in a minute. And an object whose class invariants do not hold is called broken. We're just calling those, if your invariants don't hold, your object is broken. So if we go back to our graph, we now have the subset of all the substances that are discardable. And then within that, we have all the subset of the substances where the invariants hold. And all that stuff in pink, those are all broken substances. We're defining those substances an object can take as being broken. So let's look at a pair sequence, which is the same as the zip vector that was discussed in the previous talk. And the idea here behind a pair sequence is it's a sequence of pairs, right? Or like a vector of pairs, except instead of storing a vector of pairs, we're storing a vector of the firsts and the seconds for whatever reason. And you'll note, especially after looking at Sean and Dave's talk, is that you need some kind of invariant here. We need to say that the t's dot size is equal to the u's dot size. That's the invariant of this particular type. So what does a class invariant imply? Three things. The first one is that unless a function's documentation says so, broken arguments are invalid. Okay? This is an implicit precondition. Whenever you write a function, unless otherwise specified, that function expects and requires your arguments to not be broken. Two exceptions to that, and that is the start of this of destructor and assignment. We will look at an example in a sec. The second rule of invariance is that class APIs may not give callers broken objects. That's an implicit postcondition. And the third is that mutating class APIs may not leave objects broken that were found unbroken. You can't just give somebody something that's unbroken and have them return it to you broken. That's not cool. Okay, so the first invariant requirement. Unless a function's documentation says so, broken arguments are invalid. We're going to look at this interface to pair sequence, and we'll see where this comes into effect. First, the constructor here. This is a copy constructor. It takes in one argument, that pair sequence that it's going to make a copy of. According to the first invariant requirement, it is an implicit precondition that the argument to this constructor needs to be not broken. Okay? If we look at pushback and we look at resize, These are member functions, so you can think of the this as being one of the arguments to these functions. That this has to not be broken to be able to call these functions, right? It's an implicit precondition of these functions. Now the destructor does not require this to be in an unbroken state, okay? It needs to be able to be called, it needs to be destructible, right? But it doesn't have to have its invariance hold, not according to this definition. It just needs to be discardable. So this operator equals, there are the star this argument to operator equals needs to, or does not need to be in an unbroken state. It can be broken. The invariance can be not held to be able to use assignment. However, the right-hand side of equality, that argument does need to have its invariance hold. These are the way these rules work. And any other function that you might write, which takes in a pair sequence, it has an implicit precondition that its invariance hold has to be unbroken. The second invariant requirement is that class APIs may not give callers broken objects. So the constructor of pair sequence, it can't produce a broken object and give that to a client. Remember, we're trying to make it so clients don't get exposed to these things as much as we can. And the third invariant requirement is that mutating class APIs may not leave objects broken that were found unbroken. So in the case of pushback and resize, if a star this comes in unbroken, it can't leave it broken at the end of these functions, right? It's maintaining the unbrokenness. And the same is true for operator equals. Anything coming into this that was unbroken needs to make sure that it is still unbroken by the end of this function. Okay, so takeaways on class invariant best practices. The first one is that you should document your class invariants, right? Pretty easy. It'll help you when you're reading your code, when you're working with the code, to be able to make sure that you meet these guarantees. If you don't document it, then, good luck. The second one is that you should check for invariant preservation of your APIs and debug builds, if it's reasonable for you, right? Doing these checks in debug builds will make it so that if somebody is breaking this, or someone after you who's not as great of a coder as you, but still can get into your code and potentially make mistakes, if you put these invariant checks in there, it'll help them realize that they introduced a bug, as opposed to finding it much later in production. And the third is to make it impossible, or at least difficult, for a user of your API to get exposed to broken objects. In the case of unique pointer, where we saw we were able to break that object, I don't know of a way that they can make an interface where somebody couldn't do that, right? At least from a compiler perspective. Okay, so we've talked about substance. Now we're going to start talking about essence. Okay, this is the second really important aspect of an object. So objects usually have a meaning that goes beyond just its substance and its invariance, right? That's not all that it's about. So the question that kind of leads us to this thought process is, what do we mean when we say two objects are the same? And to illustrate this, we have a rational class. Okay, a rational class has a numerator and a denominator. And for those of you who are paying attention, you'll see right away that we need an invariant here, right? Because the denominator can't be 0. So let's go ahead and add an invariant. The denominator can't be 0, and because we don't want to expose our clients to broken objects, we take the data members here and we make them private. And presumably there's an interface on top of all this. Okay. Another observation is that objects of this class, the intent is to represent rational numbers, right? We're getting that just from the name of the thing. But it's really an important aspect of this in order to be able to understand this class and what it's trying to do. So if you have a rational where numerator is set to 1 and denominator is set to 2, we kind of know that this is trying to represent the rational number 1/2, okay? So we could also say that the essence of a rational in this state is 1/2, or the value of a rational in this state is 1/2. So here we have this circle, which is all the possible substances of a rational, and here we have the particular substance where the numerator is set to 1 and the denominator is set to 2. Well, this maps to 1/2, okay? It has a correspondence with the thing that we're trying to represent. And over here we have numerator set to 1 and denominator set to 3, and we know that this maps to 1/3. And what about this one with numerator set to 2 and denominator set to 4? Well, because we're talking about rational numbers, this actually maps to 1/2 too, right? Both of these things. So two objects with different substance can have the same essence, right? And we have this mapping between substance and essence. And I don't want you to think that this is only true for like mathematical classes. This could be something like color, right? Here we have substance on the left, and this is mapping to Adobe RGB space essence on the right. So here we have different substances mapping to particular colors on a color triangle, or what is that thing? I don't know. Now we can define value types. Value types have substances that map to values. Easy enough. And an object has a value if its substance maps to a value. Now we're going to look at our rational class now that we understand that it has an essence, okay? What do we do with a class that has an essence? There's like good practices around this. The first one is you should document the values that the class represents. So in this case we say a rational number, right? There's not much more you need to say, and you can add to it a Wikipedia link to a very precise definition of what a rational number is. So we're giving a very precise sense of what the essence of this class is. The second aspect is that your external interfaces should be primarily documented in terms of the values. So in the constructor here we say, create an instance with the value a over b. We're not talking about data members or anything. We're talking about this class as if it were the thing that it's trying to represent. And similarly, we have the operator plus here, and our comment is returns the sum of a and b. If you don't know what the essence of this thing is, then you're not going to have the context to understand what's being talked about when you talk about sum of a and b, right? Now your operator double equals. This returns whether or not objects have the same value. Do two objects have the same essence? Do they have the same value? And then we have the observation that we made earlier is that value types can sometimes represent the same value in multiple ways. So here we have auto A equals rational 1, 2, auto B equals rational 2, 4. A and B have the same value, so operator double equals better return true. And how do you implement that? I'll leave that as an exercise to you all. Hopefully you remember your high school fractions here. One other observation is that broken objects have no value. If the denominator here is set to 0 because you're in the middle of a member function or whatever, that particular substance has no value, right? It only has a value if the invariants are holding. So value types. Most types are value types. These are the types that you interact with every day all over the place. Don't think it's a mathy thing. It can be a button. It can be a spaceship. It can be all different kinds of things. Those are the things that you work with. Those are value types. There are non-value types out there, right? If you consider like a type trait or various meta functions, things like that, where the instances don't really have any meaning, right? We're just using types as a tool for something else. Those, we can call those mechanisms, right? Those are not value types. But the ones that you normally deal with are value types. So all this stuff applies. All right. We've talked about substance. We've talked about essence. And now we'll discuss the third thing, which is meaning. What could that mean? An object is meaningless if the most that is known about its substance is that it's discardable. Okay? At a particular point in code, you know stuff about an object, right? You might know that something is set to 3 or whatever. That's something you can say about it. If you don't know that, if you don't know anything about the objects, then we say that it's meaningless. So let's look at some meaningless objects. So here we have int I, right? Int I, and then we assign I equal to 3. In between those two statements, I is meaningless. What can we do with I there? Well, we know that it's discardable. We can destroy it. We know that we can assign to it. So we have this discardable property, but what else do we know? Do we know that its invariants hold? Not really. Do we know anything about its value? No. So we're calling it meaningless, right? After I is assigned to 3, now we see that I is not meaningless, right? It has a specific value. We've given it something more than just knowing that it's discardable. So looking at the STLab exception safety classes is going to help us illustrate this point. So we have minimal exception safety, which says that partial execution of failed operations can result in side effects, but all objects under mutation must be discardable. Okay, we'll look at an example, so don't worry if that didn't parse very well. Or we have the strong exception safety guarantee, which says that partial execution of failed operations cannot result in side effects, and a consequence of that is all objects under mutation must have their original values from when you entered into it. So here we have an example. Here is a function called minimal. Okay, it takes in a foo reference. And this has the minimal exception safety guarantee. Okay, fine. Here is a function called strong. This one has the strong exception safety guarantee. So now let's look at these code snippets and see what we can say about the meaningfulness or the meaninglessness of an object. So the first snippet, we assign x to something, we call minimal of x, we try to call minimal of x, and an exception is thrown, we're in that catch, okay? What can we say about x? Well, the only thing that we can say about x is that it's discardable. We don't know anything else about it. So x is meaningless in this case. Here we do it, but instead we call the strong function. We assign x right above the try block, right? So when we call the strong function and it throws an exception, we know that x has the same value that it had when it was assigned to right before calling the strong function. So x is not meaningless in that situation. And exceptions are not the only way that an object can go from being meaningful to being meaningless. There's one other way. And that is moving. Okay? Here we have some object A of type foo, and we say object B of type foo, we move construct that with stood move of A. Okay, so A is in the move from state. Now, unless there are other guarantees provided by foo that says what move from states are, really the only thing that we know about it is that it's discardable. We know we can assign to it, we know we can destroy it. It could have a value, right? It very well might have a value with all the invariants met, but we just don't know that at this point in code. So we call it meaningless. So meaningless objects. Meaningless objects have a substance. All objects have a substance, okay? At all points in time. Meaningless objects are discardable, generally. They may or may not be broken, and they can be made meaningful again through assignment or other setter operations. So the intuition here is that if you're observing a meaningless object, that's some kind of a defect in your code. You shouldn't be looking at things that are meaningless. It's not like well-defined what's going to happen there. It doesn't make any sense. So don't do that. This sense of meaningless gives us this other rule. And it's unless a function's documentation says so, meaningless objects are invalid. That's an implicit precondition. Now, this is the exact same sentence that I gave you before about broken objects, but we're also applying this to meaningless objects. And of course, the star this of destructor and assignment are notable exceptions to this rule here. Okay. We've been exploring some words, right? We've talked about valid. We've talked about what an object is. And remember the three aspects of valid. The first is that it creates some kind of a separation of two different categories, the valid and the invalid. That there's an aesthetics, that one of these is better than the other one. Makes us have less churn in our stomach when we see it. And there's also this subjective aspect to the whole thing. And with objects, we've seen that there's a substance, right? There's a line around what defines an object. This beautiful idea that separates it from everything that is not it. But it's not just the substance, right? There's an essence to an object, something beyond its itness. And then finally, there's a meaning, which is like a purpose, like something else, what it knows about this object. And often when you really think deeply about things in computer science, or really in any field, you start to touch upon some bigger principles of things. And I think that this is definitely the case with this work here, especially when we start talking about objects and the three aspects of an object: the substance, the meaning, and the essence. So if you take it and you think about it, the substance is defining existence, right? Am I? If there is substance, then there is something there, right? Something which separates it from everything else, something special. If there's an essence, it's answering the question, what am I, right? Are you something beyond your substance? Is there something more to it than that? And then meaning is, why am I? What's this? Is there a purpose, right? Is there a meaning? Is there something beyond just I am, and I know what I am, but why, right? And one of the ways that you can think about this is it opens up a question about artificial intelligence, which I think is really interesting, right? So what am I? I'm a person, right? I am made up of some fleshy stuff, and there's some kind of a distinction between me and all this other stuff out there, right? So I am. But I am not just this fleshy existence, right? There's these thoughts in my head, right, that makes up me. Like there's meanness in the configuration of these neurons in my head that gives me meanness. Now, what if an artificial intelligence can be trained on all kinds of stuff about me? What if it sees everything that I see and monitors all my reactions and is able to make the correspondence and act exactly as me, right? Or maybe it does a scan of my head and is able to model this and be able to replicate potentially the essence of what I am. That's not the same substance as me, but could it be the same essence as me? I have no idea. So So anyway, I just thought that was an interesting thought. This is the conclusion of my talk. I will definitely be happy to take questions. I do want to point out that this C++ at Adobe website has just come out. We worked really hard on it. On there you can see careers, you can see the events that we're attending. There's training, so if you like the Better Code series of talks, I think we have like 4 or 5 talks actually uploaded up there where you can go see them on YouTube if you're interested in seeing that training. And with that, I will be happy to take any questions.
Hi. I have a question. Like, it's been a while since I read EOP, but the beginning has some of the similar ideas. What would be the difference between what you suggest and what they suggest? If you know.
It is very similar, right? So I was looking at EOP when I was starting to do some of this stuff, but I forget the exact terminology that's being used. But especially in terms of the idea of a value type, and I forget if it was called like a nominal object or
Partially formed.
What's that?
I think partially formed was the term.
Well, so setting aside the partially formed thing, the idea that we're trying to represent values is definitely in there. The partially formed state, I think, closely relates with the idea of a broken object. Or not broken, but a discardable object. Yeah. But I don't have like an in-depth answer ready for you, because it's not fresh in my mind.
Okay, thank you.
Yep.
Hey, thank you. It was a very interesting talk. So one thing that I'm wondering about, and this is also something that I was wondering about in the previous talk. So I really like this idea of object discardability. I was just recently in a position where I was writing a library, and there were kind of like corners of my API surface where if something goes wrong because of properties of the type or whatever, I will wind up in a situation where I have an error that is truly unrecoverable and it will make my object broken. And so I really like kind of having this escape hatch to say, because this happens in C++, like there's generally a problem of like throwing moves and stuff like that, like how do we deal with these things? And so I like having the verbiage for that. But at the same time, it seems like there is also still real value in something like the basic exception guarantee. And so I guess basically, in all the slides that I've seen here thus far, the minimal exception guarantee has been replacing the basic exception guarantee. Like, is there not space for these things to kind of coexist? And I guess I'm just wondering, like, are you guys suggesting that this replaces the basic, or is this just a new kind of exception guarantee that we might think about?
Well, I'll give my opinion on this. I haven't talked a lot about it with the other folks on the team. But one observation to make is that everything which meets the basic exception safety guarantee also meets the minimal exception safety guarantee. And the question is, if you're dealing with exceptions and something is thrown, what you do with the resulting object, right, that could have been messed up, doesn't change based on whether or not it has the basic exception safety guarantee or the minimal exception safety guarantee. Either way, looking at it is going to be not the right thing to do. So really, I think that I don't really see a use of having this intermediate basic exception safety guarantee. I just don't know how it would change anybody's code. So I think the minimal is a more useful concept to use.
It'd be interesting to talk more about this at some time, but I'll leave that here for now. Thank you.
Yeah.
Hey, one thing that I noticed is in your model of meaningfulness, you said that operations that transition to this, that can transition to this meaningless state, they gain this implicit precondition that you cannot do anything except destruction or assign to it when it's meaningless. This is a different model than what we have in the C++ standard library, where we say if it doesn't have precondition, you can even use it, for example, you use the operation on a move from object. Do you have any thoughts on that? Like, are both models equally valid? Is the standard library doing things wrong here? What? Yeah.
So I think that it really boils down to if you have something which does it the way the standard library does it, it still has an unspecified value, right? You still don't know what value it is unless it gives more specification in the particular operation. So there's nothing you can really do with it. So applying this is actually being just a little bit more explicit about the things that you already should not be doing. I don't know if that makes any sense. And I think that if we recast the standard library, if we did it again today, given what we know now in this like mental framework, I think we probably would not have done it that way, because this actually leads to a lot of efficiency gains that wouldn't be available if you had to have that requirement of validity.
Thanks.
Yep.
Hey, I've got a question about terminology. So you gave three ways of classifying objects, like discardable, not discardable, unbroken, broken, and meaningless, meaningful. And the difference is that with the unbroken, broken one, the valid side, that's valid for general use, the word is unbroken. So that's excluding what the object isn't, that it isn't broken. Do you have a word that describes what the object is?
It's a keen observation, and it's one that I've definitely thought about. So another way of saying unbroken is that the invariants hold, right, if you want to put it in a positive way. But it would be nice to have a nice, succinct, beautiful word for that, but I don't have one.
Okay.
If you have any ideas?
I will tell you if I think of one.
All right.
I'm very conflicted about your talk. I liked many parts of it, but there's one aspect of it that I find very deeply disturbing indeed, and that's your introduction of the word essence. I began looking to see what else besides value you ever meant when you used the word essence, and I never found one. So my question is, what advantage is there to introducing a word like essence when you only mean value?
Yeah, so I think that value and essence in my model are the exact same thing, right? So the question is like, why introduce essence? And the reason that I like that is because it very neatly corresponds with substance. Substance and essence are like philosophically very like well understood concepts, and their relationship is actually identical to what we're doing here. So I like that dichotomy. But if you prefer to just use value and not use the word essence, like I'm totally cool with that.
I think that goes to the heart of my complaint, that it's philosophical. Because if I asked you to write a function called getValue, and you can read an address, you can give me a value. Now I ask you to write a function called getEssence. What do you return?
Well, I think that behind that question, the idea that you can have a function which is called getValue is kind of like a misunderstanding of what these concepts are. A value is not like a data member. You don't get a value, right? A value is describing what something that exists is. And I'm sorry you don't like philosophy, but there's nothing I can do about that.
Okay.
All right.
I would also want to ask for clarification of terminology. So when you said state is basically something that the object owns. The word owns usually refers to like owning pointer versus non-owning pointer. You own something if you can destroy it. So in this sense, for example, what's the state of the string view? It doesn't destroy, the piece of the string it points to. So is the state of the string view just the two pointers inside, or is it also the piece of the string that it points to?
I haven't thought about that too deeply, so I don't want to give an answer off cuff and then be wrong, but I have to think about that and get back to you. Yeah. There are a couple ways of looking at it, really.
Hey, thanks a lot. Great talk. So in the language, we already have these qualifiers such as no except to help reason about exception guarantees, and const or R-value reference qualifiers for arguments to specify about their some part of their states. Would you think that it makes sense to have more qualifiers to specify like the minimum or strong exception guarantees for functions, maybe the meaningfulness or meaninglessness of arguments, because you've like shown that static analysis could basically know when something might be meaningless?
Yeah. So my understanding is that it would be possible to make a static checker that makes sure that you don't do any observing operations on meaningless objects, right? But you might need some annotations for exceptional circumstances. So one of the things that our team is working on is this programming language called Hilo, which really makes it impossible to do some of these things which we're saying don't do on these slides. So I think it's definitely possible in a new language, but if you're trying to put that into C++ somehow, you might run into difficulty of just being overloaded with complexity in the language. But there could be a simple, elegant solution. I would definitely be interested in seeing anybody who wants to do like research in that and try to see where it takes them.
Hey, so the standard says that for a standard library object that is moved from, it is left in a valid but unspecified state.
Mm-hmm.
So is this a name collision with your interpretation of valid, or do you suggest that it should be left in a meaningful state?
I think it should be left in a discardable state, right? And so when you talk about the different kinds of validity for an object, I would say to be really specific there, what I'd like to see is that a move from object is left in a discardable state. And everything just still works. It's just we're being a lot more precise about what exactly is okay, what can be done on that object.
Thank you.
Yep. All right, we are out of questions. Thank you very much.